Okay, we are back talking about stationary stochastic processes, which is fun. It's more fun than you thought it. It's more fun than it sounds, isn't it? Stochastic processes. You know, the funny thing about randomness and stochastic processes is that they have a deterministic side, right? We talk about random variables, yet even though we talk about random variables, um, that the mean is deterministic. The variance is deterministic. We're talking about stochastic processes. The mean is deterministic. The autocorrelation is deterministic. So fascinatingly, I think it's always fascinated me that we use deterministic functions, deterministic ideas, and apply them to stochastic processes. And we apply them very, very well. I think what I'll do is I will start with looking at the homework I would like you to do. And let me get rid of my dirty laundry here in the background. There we go. And here's the homework that I would like you to do. Let's just go over it a little bit. I think you'll enjoy these and hopefully learn some things. So one is the confidence intervals. One of the things that Claude Shannon, the father of Shannon information theory, did is he went to a casino wearing one of the first wearable computers, and he and another employee of the Bell Labs, and I forget the other employee's name, figured out a way to beat the roulette wheels because apparently they weren't fair, and they made some money. So this is just a simple example of a roulette wheel having 37 slots, and 2 of them are green. If you've ever seen a roulette wheel, right? They have red, black, red, black, red, black, red, black, and then they have 2 which are green, which is a 0. I think a 0, if I recall right, and a 0, 0. And so what you do is you do 10,000 tries, and a bowl rolls into green 735 times, and generate a 95% confidence interval around the sample average 0.738. You notice that 0.0738 is 735. Whoops. Okay, wow. I did a typo here. That this is the first number divided by what, 10,000. Okay, so that's the point average. That's the average, and you're trying to estimate the mean, the underlying mean. And we know that the underlying mean, if the roulette wheel is, I was going to say Ferris wheel. Okay, that's different. Ferris wheels and roulette wheels are very different. We know that the probability of getting in the green here is 2 out of 37, but we're going to assume that we don't know that. So in evaluating the confidence interval, do not use the fact that the true value is 2 out of 37. And then ask the question, does the true value of this probability, 2 out of 37, lie in the 95% confidence interval? And then you can ask the question, do you think that the roulette wheel is fair? And the idea I'm shooting for here is that if the 2/37 lies within the confidence interval, then yeah, it's probably fair. And if it doesn't, no, it's not fair. Okay. So that's one of the problems that I would like you to do. The other one is in Poisson processes. And this is a simple problem. Cars go by at a point on University Avenue at an average rate of 1 car every 2 seconds. What is the probability no cars go by in 1 second? So that's applying the stochastic process, which is a Poisson process, and figuring out this probability. Now, the next one is kind of interesting. No cars go by for 5 seconds. So you're sitting there, and for 5 seconds, no cars go by. And you ask yourself, what is the probability no cars go by after 6 seconds? In other words, if you wait another second, what is the probability that a car will go by? Do you get the question? And I'd like you to compute this. And this is a very nice and a very classical problem. And you might be able to find it on the web, but it's very interesting.
So is that just the probability of the single next second, or is it the probability of the 6 seconds total you're looking for there?
That's the question I'm asking you.
Okay.
Okay. I'm going to ask you, does the no cars going by for 5 seconds, how does that contribute to your final answer?
Okay.
Okay. Interesting question, don't you believe? And then I'd like you to perform a problem in stochastic processes. So here, a sequence of IID uniform numbers on 0, 1. And you can generate this by flipping a coin, right? Or by using a random number generator on Excel or MATLAB or Python or whatever your favorite computer is. So you can generate a big sequence of zeros and ones. Then what you're going to do is you're going to convolve it with a rectangle width of length 100. Now, in doing this, we're going to assume stationarity. So we assume this 0, 1 sort of thing goes on from minus infinity to infinity, so that there's no transient. See, if you generate like a million results, there's going to be a transient to the convolution at the origin and then at the end. And I don't want you to consider those transients. We're just assuming everything is stationary here. So a sequence of IID uniform random numbers on 0, 1, and then you convolve it with a rectangle function of length 100. And this new resulting stochastic process is called capital X, as you can see here. And my question to you is, what is the mean autocorrelation and autocovariance of X, this new stochastic process? And you should be able to figure that out. And then ask ourselves, is X stationary in the wide sense? If you recall, the wide sense, as we introduced last time, and we'll talk a little bit more about this time, means that it's stationary in a very, very general sense. And then is X Gaussian or close to Gaussian? Let me ask you this question, and we can discuss it right now. Do you think that if you convolve an IID sequence of 0, 1 with a large window, that the resulting stochastic process is going to be Gaussian? Well, what are you doing? For every window position, what you are doing is you are adding up a number of uniform random variables. What is that going to give you? So you have a bunch of uniform random variables, you add them all up, and that becomes your new point in your new stochastic process, right? So what is going to be the distribution of that point? Central limit theorem. What is going to be the distribution of that point?
Gaussian.
Gaussian, right? You're adding up a bunch of IID random variables, and we've said by the central limit theorem that is going to be Gaussian. So we know that, at least on a pointwise way of doing things, that we're going to have a Gaussian probability density function. Can you convince yourself that it is Gaussian otherwise? So that's what I'd like you to do. And let's look at that and talk about it Thursday, and then have it due next Tuesday. So please take a look at that and see if you have any questions for next time. Any questions at all? Okay. I don't know, looking at you guys, it's hard to tell whether or not the screen's frozen. But, I saw Adam move. Okay, we're good. Okay, he's going back and forth in his chair a little bit. Okay, so that's all well and good. So let's continue with our idea, the idea that we had of stationary stochastic processes. There was, first of all, stationarity in the strict sense. That's really rough, because that means that the statistics of a stochastic process, if you have a stochastic process, the statistics is independent of your choice of origin. Equivalently, if you take, I have 4 fingers here, if you take 4 points of the stochastic process at some point in time, and you look at the statistics there, and then you take those same 4 points, you don't change the distance between them, but you move them down the axes a little bit, and you look at the statistics of those 4 points, they're going to be exactly the same as it was of the original 4 points. Remember, stationarity is trying to assert the idea that the stochastic process does not change its character with respect to time. And in engineering, we come across these processes all the time, from background hum to floor noise and RF measurement, to white noise, to shot noise, all sorts of processes are stationary in the sense that they don't change with respect to time. But determining all of those statistics is really rough. I mean, determining the fact that you have to have the same statistics here as you do over here, and you have to do it not only for 4 points, you have to do it for 3 points or 1,000 points if you moved over. And that's really rough to do, of course. So therefore, we wanted to get a little bit more lax definition. And this lax definition was stationarity in the wide sense. So in the wide sense, in the sense that it is a sloppy, it's a sloppier definition of stationarity. It's a sloppier way of saying that the stochastic process does not change with respect to time. So with that, let me get up the slides and begin my pontification. Excuse me. So we saw last time, as I try to get full screen here. Yeah, we saw last time that if x of t is stationary in the strict sense, the mean is constant for all time. I mean, if a stochastic process is not changing with respect to time, the expected value of the stochastic process at one point is exactly going to be the same as the expected value of a stochastic process at another point. The other thing is that the autocorrelation is a function of the distance between the points only. So therefore, if we look at the expected value of the second moment here, or the second order statistics, x of t times x of tau. Now, what is that? That means that you have a stochastic process, and you're looking at the stochastic process at some time t and at some time tau. And what we're saying is that the autocorrelation is only a measure of the distance between here. So if we go over to the stochastic process later, and we say, let's say t plus 47 and tau plus 47, you can see that these are simply points which are shifted versions of the previous points, that the autocorrelation between these 2 points is exactly going to be the same as the autocorrelation between these 2 points. Again, trying to capture the idea that the stochastic process does not change with respect to time. Now, these criteria are applicable to stationarity in the strict sense. In other words, the statistics do not change with respect to time. But there's ways that you can get wide sense stationary stochastic processes that are not stationary in the strict sense. So we see that the idea of stationarity in the strict sense, and I drew this Venn diagram last time, is subsumed in the idea of wide sense stationary stochastic processes. Okay. The other thing that happens, it turns out that, you remember the autocovariance, in other words, C sub x of t tau? This also, if you have a stationary stochastic process, is, whoops. Let me try to make that, no, I can't do that. Is also going to just be a function of t minus tau. Okay. I would add, we're not doing it here, but if you ever come across complex stochastic processes, and you do this a lot in optics and antenna theory, that this second x of t is conjugated. This is the definition of autocorrelation for complex stochastic processes. It's the expected value of x of t times x conjugate of tau. And I'll point this out as we go on. Okay, this is basically what we said. If x of t is wide sense stationary, then its expected value is equal to a constant, or the mean of the stochastic process, and that mean is not a function of time. And also that the autocorrelation is only a function of the distance between the 2 points. So let's look at this new idea of stationarity in the wide sense. First of all, recall that the expected value of the power as a function of time is equal to the expected value of x squared. Now, if we were having a complex stochastic process, this would be the expected value of the magnitude of x squared, but just for real processes, it's the expected value of x squared. This is well and good, but the interesting point is that in general, let's just talk about this. In general, the autocorrelation at t and tau is equal to this expected value, right? Expected value of x of t to x of tau, that's by definition. But r sub x of t and t, say we take both of these values and we evaluate it at tau is equal to t here, then we get the expected value of x squared, and that's the expected value of the power, right? So the autocorrelation, when you evaluate it at the same point, gives you the expected value of the power. Now, to this point, we've made no assumptions about stationarity. This is always true. The expected value of the second moment can change with respect to time, and the power can change with respect to time. You know, if you stick your fingers in a light socket and you feel the power and then somebody turns it off, you know that the expected power or the power has changed with respect to time, don't you? So if r sub x is wide sense stationary, let's apply that criterion now, then the expected value of this is equal to r sub x of 0. Remember, r sub x is just a function of t minus tau, right? Correct? That's the definition of stationarity. It's just a function of t minus tau. Well, if t is equal to tau, which is what we're requiring here, then it turns out that the r sub x of 0 is equal to the expected value of x squared of t. And it also says that r sub x of 0 is equal to the expected value of the power. And since the process is stationary, this power is going to be a constant, which we can call P sub r. In other words, the power, the expected value of the power does not change with respect to time. It's always exactly the same. So again, we mentioned it before, if you stick your finger in the socket of an electric outlet, this is what you feel. You feel the expected value of x squared. We've worked this before, but let's go through it again with the idea of stationarity. We have a stochastic process. I'm going to assume here that A is deterministic. Okay, so A is known. And capital Phi, the fat guy, fat theta is equal to the random variable. And this is what you would expect. If you looked at the sinusoid, which came out of the wall socket, you know it would be a sinusoid. You know the amplitude because you know the expected voltage of the output. But the phase you wouldn't be quite sure of, right? There's no way where you look at the phase of the voltage that you get from a socket. You don't know what the phase is. So we can treat that as a random variable. It can be anywhere from minus pi to pi or 0 to 2 pi, whatever you want. Well, first of all, the expected value is 0. You can see that right away because you have the stochastic process, which kind of goes like this, right? And the phase determines, your phase is determined by where this goes at the origin. But you can see that the positive voltage eats up the negative voltage and the overall expected value is 0. And if you wanted to, you could figure this out. How would you figure this out? You would do the expected value of x is equal to A times the expected value of the cosine of omega t plus theta. And that, of course, is equal to A times the integral of the density function, right? The probability density function for theta is, say, between minus pi and pi. Therefore, it has a height of 1 over 2 pi. And so it's equal to A times 1 over 2 pi times the integral from minus pi to pi of the cosine of omega t plus theta plus little theta d theta. Again, we're integrating with respect to the random variable here because that's what we're doing, the expected value. Well, you know that if you take a sinusoid and you take a integral over a period of a sinusoid, this is an integral over a period of a sinusoid, that this is equal to 0, right? And we can see this graphically up here where the positive part cancels out the negative part. So the expected value of the stochastic process is equal to 0. And the autocorrelation, which we worked out before, is given by this expression. Now, you notice that just very naturally in this expression that the t minus tau comes out as part of it. So therefore, we have an autocorrelation function, which is just a function of t minus tau. So this is stationary in the wide sense. So this x of t is an example of a stochastic process that is stationary in the wide sense. So that means that the r sub x of tau, this is the autocorrelation, a squared over 2 times the cosine of omega tau, and that's equal to and so this is the result. And r sub x of 0, the autocorrelation at the origin, is the expected value of the power, which in this case is a squared over 2. And again, we pointed this out previously. This is the RMS voltage of a sinusoid that you learned way back in introductory circuits as a over root 2. Now, here is the interesting thing about characterizing a wide sense stationary process. You remember we compared this to a linear time invariant system? What did you need to know in order to characterize the linear time invariant system? You needed two things. No, you needed one thing. You only needed the impulse response. That's all you needed. And then you took home that impulse response, and then any time that you had that impulse response, you could take an arbitrary input, you could convolve it with the impulse response and get the corresponding output, right? So that's indeed what we get for the linear time invariant system and how to characterize it, how to model it. For a linear time invariant system, we need two things. We need, first of all, the expected value of x, in other words, the mean of the stochastic process. And the other thing we need is the autocorrelation function. Then, in terms of the wide sense stationary characterization of the stochastic process, we have done what? We have characterized the stochastic process to the degree that we would like. So this is really good stuff. And what does this mean? How can we use that? Well, for first and second order statistics, it's no problem at all. We have t plus tau over here. So the distance here is tau. And so we know the autocorrelation of this number with this number, right? We also know the mean of this number, the expected value of this number. What's the expected value of this number, this statistics? It's equal to m, right? Because all of the points have an expected value of m. And the autocorrelation between here and here is equal to, I don't know, whatever it is, but in order to figure out that autocorrelation, you just go to here, say this is tau is equal to 3. You go over here to tau is equal to 3. And this point would be the autocorrelation between these two random variables. You get that? And the other thing which is true here, that if we go to some other values, say t minus 8 and t plus tau minus 8, I don't know. Well, that probably, It's probably graphically not the same, but I hope you'll get the idea. In other words, we take this point and move it to the left by 8. We take this point, move it to the left by 8. Well, what's the autocorrelation between these two random variables? Well, in this case, the distance between the two random variables, is still what? Is still tau. And so tau is equal to 3, right? The distance here is tau is equal to 3 also. So what's the autocorrelation of these two random variables? It's just the difference between the two. We can come over here for tau is equal to 3 and read off what the expected value is for, this would be the expected value of x of t times x of t plus 3, right? So that's how we can obtain that. But the characterization, again, of the Widesense stationary signal is totally defined if you know the mean and the autocorrelation. And for a lot of engineering purposes, we'll find out that these second-order statistics, this autocorrelation and mean, is sufficient to do a lot of things that engineers are interested in. Now, here's a question. How would you estimate this empirically? Say you have a stochastic process, and this is something which is stored in a big vector. And this is stored in a big vector in Python or something like that. So you have this big, long sequence of numbers. Let's assume that it's Widesense stationary. How would you estimate the autocorrelation? I'd like you to think about that. And then next time, I don't know, maybe I'll give it that as a homework problem. How would you estimate the autocorrelation if you were given a string of signals? Or I think more straightforward, an ensemble. Do you remember the idea of ensemble and ensemble averages? I think empirically determining the autocorrelation is something that you could do there more easily. So I'd like you to think about empirically generating the autocorrelation given an ensemble of samples of the stochastic process. Okay? So Widesense stationary random processes autocorrelation properties. This is what defines these are different characteristics of the stochastic process. If we have a Widesense stationary stochastic process, there's certain laws that it must go by. First of all, we've already established this. We've established that the autocorrelation at the 0 is equal to the expected value of x squared, which is equal to the average power. Another thing which is interesting is that the autocorrelation is an even function. Because if you think about it, if you take a point and you go this distance tau, the autocorrelation between this should be the same as you take this point and go in the other direction a distance tau, right? The distance between the two is exactly the same. And the proof of this is very, very simple. The autocorrelation is given by the expected value of x of t times x of tau. And you can see, since you can commute the x of t and x of tau, yeah, it means that you can replace the t's with the taus and the taus with the t, and you get this symmetric result. Now, for complex systems, I'll just mention this parenthetically, this is conjugated, and it turns out that the autocorrelation is conjugately symmetric, which means it isn't an even function. But if you do flip it around and conjugate, you get exactly the same thing. We see this a lot in Fourier analysis, and this will become important later. But again, if you have real processes, you don't have to worry about the complex conjugates here. So let's see what else. One of the other ones is that the autocorrelation is always maximum at the origin. Now, here's the kind of the way that I think about it. If you have a stochastic point, some point on the line, and you want to maximize the correlation between that point and all the other points, doesn't it make sense that the autocorrelation is going to be maximum when you autocorrelate something with itself? Yeah, when you autocorrelate with something with itself, yeah, you're going to get a big correlation. But if you correlate this with something which is at a different point, you're probably going to get a smaller number. That's the way, at least I think of this intuitively. So we see that we have stochastic processes, and we have this would be an okay stochastic or an okay autocorrelation. I think one that's turns out a lot is kind of a damp sinusoid, almost like a sink or a damp sinusoid. So you see a lot of autocorrelations like this. Notice that both of these have here as a maximum. Now, to prove this, we have to go back to the correlation coefficient, something we proved about the correlation coefficient, and that was the correlation coefficient was always less than or equal to 1. You recall us talking about that, I hope. Well, this is the definition of the magnitude squared of the correlation coefficient. It's the ratio of these two things. And on the top here, we see that this is what? This is the autocorrelation squared, right? Expected value of x of t plus tau x of t. So this is the autocorrelation squared. These are the corresponding variances of the stochastic process. And that must be less than or equal to 1 because the correlation coefficient is less than 1. And then if you simply solve this, you get that the expected value of this is less than this. And this is true, by the way. This is true, by the way, even if x of t is not zero mean. It doesn't have to be zero mean. So this is the what? The square of the autocorrelation, and this is the corresponding variances. So the autocorrelation is always less than or equal to the value of the autocorrelation at the origin. Here's another property. If r sub x of tau is equal to r0, let me draw a picture here. We always say that the value of the autocorrelation at the origin is maximum, but that does not mean that the autocorrelation cannot appear elsewhere as the maximum. So this might be the maximum. This is still the maximum. This is the r sub x of tau. So, okay, this meets the fact that we have a stationary stochastic process and its maximum at the origin, but that maximum is replicated here and here, okay? And that is a possibility. Well, if indeed that is a possibility, if there is a replication of the maximum, then we can prove that r sub x of tau is a periodic function. In other words, this autocorrelation appears here, it appears here, it's going to appear over here, it's going to appear forever and ever because this is going to be a periodic function. Consider, for example, the sinusoid with a random phase. You'll notice that x of t is perfectly correlated with itself if you increase t to increase the cosine by 2 pi, right? Because if you increase the cosine by 2 pi, you get exactly the same as if you didn't increase it or shift it over by 2 pi. And what we showed is that r sub x is equal to the magnitude squared of a over 2 times the cosine of omega tau. So you'll notice here, this is an example. This is an example of a stochastic process that has its autocorrelation, a squared over 2 is the maximum. But that maximum is replicated at different points. And this indeed is periodic. This is a periodic stochastic process, and the autocorrelation is periodic likewise. So those are 4 criterion for stationarity, right? One is that the expected value is equal to the expected value of the stochastic process is equal to a constant. The other one is that the value at the origin is the value of the autocorrelation of the origin is always equal to the constant expected value of the power. And then I forgot what the third one was. Oh, yes, that the autocorrelation is a relative maximum. And the last one is that if you do have a replication of the maximum at the origin at any other place, then the stochastic process must have an autocorrelation that is periodic if it's a Widesense stationary stochastic process. So these are 4 characteristics of stochastic processes. I drink iced coffee a lot. What you can do with iced coffee, this is really interesting. If you have coffee left over from the previous day, you put a little bit of half and half in there, some Splenda, and I use some pumpkin spice powder to put in there, and it really tastes good with some ice. Because you can't taste the coffee anymore. It's all the sweetener and the spice that you put on it. Okay. So with that, I gave you a homework problem where I gave you those number of different IID random variables that you were to convolve with a window, and I asked you to compute the autocorrelation of it. It does turn out to be a Widesense stationary stochastic process. So I would like you to generate the mean and the autocorrelation of that stochastic process. And that is not going to be periodic. You're not going to have a periodic result in this case. Now, there are other types of processes that we can generalize on. One is a cyclostationary stochastic process. What is a cyclostationary stochastic process? Well, let's say, for example, you're taking the power load from a power plant, and what you get at every point is you get a certain amount in megawatts, okay? And you go from midnight one day to midnight the other day. Probably at midnight, you have a minimal use, right? If you look at the next day, what are you going to get? You're going to get something that's probably different, but it's going to kind of look the same, right? And then if you look at another day, it's going to be kind of the same, right? It's going to be different, but it's going to have the same sort of characteristic. Cyclostationary stochastic processes basically said that the statistics here are going to be the same as the statistics in this period are going to be the same as the statistics in this period. So if you're looking at a repetitive stochastic process over a certain time interval, it could be that you could model it as a cyclostationary process. And just like before, we can talk about cyclostationarity in the strict sense. That means that every 5 million points we choose here has to be the same in terms of the probability density function of the all of the equivalent number of points that we find here. And that's a lot to do. But we can also talk about cyclostationary products in more of a sloppy sense, if you will, in a wide sense. So there is cyclostationarity in the strict sense. All the statistics are periodic. So if you have statistics at some point in time, at these points in time, for example, and you move over MT, so this, if you will, is M periods. Unfortunately, we're using M for median here, or mean, and we're using M for an integer. But you go over M periods, and you have all of these stochastic processes here. You're going to have all of the same sort of statistics over here at the same points moved over by M periods, and that better be exactly the same. That's stationarity in the strict sense. And this has to be true no matter how many points you choose and where you choose the points. Pretty rough thing to establish. It can be established in some senses and some cases, but in general, it's not going to be the same. So this is this is cyclostationarity in the strict sense. Again, kind of difficult to use. So let's get a little bit more sloppy and let's talk about cyclostationary in the strict sense. Let's look at this A cosine omega t. Okay, this turns out to be, if you look at A here, this turns out to be cyclostationary in the strict sense. And the period is equal to t over 2 pi. And that is something which we can prove to be cyclostationary in the strict sense, but it's I'm not going to go into the details right now. So Widesense stationary Widesense reset. Widesense cyclostationary stochastic processes. The requirement for the Widesense is that the mean must be independent of the period that you're looking at. So if you look at a period of stochastic processes here, and you look at the period of stochastic processes here, and you look at the mean of the stochastic processes here, and you generate the expected value of these random variables. So you get, this is the expected value of these random variables. If it is Widesense cyclostationarity, then the expected value in this period is going to be exactly the same as this expected value in this period is going to be exactly the same as this period, and it's going to be exactly the same in this period. So all the expected values are the same within the period. So that's one of the criteria. And you can see its flavor with Widesense stationarity for regular stochastic processes, that things don't change. And the other thing is that the autocovariance is a function of, the autocovariance is periodic with a period of nt. So this is equivalent. This is equivalent to what we talked about in terms of stationary stochastic processes of the normal type. Okay, are there any questions at all on that? Okay, hearing none, let's go on to a different result. And this is going to be a very, very interesting result for reasons which you'll see. It's very practical too. Okay, that's not what I want you to see. This is what I want you to see. These are so-called ergodic theorems, and we can talk about so-called ergodicity. This is a property which you can apply of stationary systems. I'm sure it's applicable to non-stationary systems, although I don't know personally any useful ergodic theorems applied to non-stationary stochastic processes. But here is the idea of ergodicity. Ergodicity means that you can determine the statistics of a stochastic process looking at one instantiation. Recall that we looked at an ensemble. What's that? What are we missing? Oh, I think I froze, or somebody froze. It's all Glauco's fault. He froze the screen.